So in our first lecture, we looked at the broad principle of the greedy method and we looked at a couple of examples. Now we will look at one very standard problem which is amenable to a greedy solution. The problem is called knapsack. So here's the formal statement of the problem. So you have some bags, say n bags, and they all contain something valuable and divisible. So let's suppose each contains some chemical. Okay. So these are all some chemicals and each of them is in a bag and each bag has a weight. Okay. So weight of bag I we can write as say Wi, and each bag has a different value. So they are all valuable items and each has a possibly different value. So this is the price of the entire bag. So Pi is the price of the entire bag of weight Wi. Now you want to carry these away, but what you have with you is a knapsack. Now a knapsack is just another term for something like a backpack. But you have only a certain amount of carrying capacity. You can't take away the entire thing in general. So you have a knapsack which has capacity m. Okay. So this m is in the same units as weight. So it might be kilograms or grams or whatever. So you can put only m grams or m kilograms of the chemicals here. And so the problem is therefore if you have more chemicals than will fit in your knapsack, you have to choose the chemicals appropriately. So what you want to choose is a mixture. Okay, so you want to choose some combination that fits in the knapsack, right? So you can't carry away more than m. And what you want to optimize, so this is the feasibility criterion, that you want to fit something of total weight at most m in your knapsack, and you want to maximize the value. So what this means is that if you look at these chemicals, for each chemical I, you will choose some fraction xi. Now this fraction xi lies between 0 and 1. So if it is 0, it means you don't take that chemical at all. If it is 1, you take the entire amount. And if you take part, like half or 1/3, it just means you take that much. So it is crucial that this thing is divisible. Okay, so you can take any arbitrary fraction. And so this is a kind of knapsack problem which you can think of as a fractional knapsack problem. Right? So what happens when you take xi? Well, you just get a proportionate value. So the value is just xi times pi. So if you take half the bag, you get half the value. So if the bag is worth 1,000,000, and if you take half the bag, you get 500,000. And what does it mean to choose a mixture? Well, this mixture now is a combination of these xi's. So you have a vector or a sequence x1, x2 up to xn telling you how much of each chemical you've taken, and each xi is somewhere between 0 and 1, indicating whether you didn't take it at all, you took all of it, or you took part of it. So here is an example. Let's think of these powders as chemicals. So we have three chemicals, 1, 2, and 3, and the weights are 18, 15, and 10, and their values are 25, 24, and 15. And let's assume that we have a knapsack of size 20. Right? So we can only carry 20 out of this 18 plus 15 plus 10. We can't take all of it. We can only take some 20 units totally, but we can divide these things up. I can take 9 of this and 6 of this and 5 of this, for example. Okay, and then get a proportionate amount of the value. So here are some feasible solutions, right? So I can take half of the first one. So I take 9 units of this, I take 1/3 of this, I take 5 units of this, and I take 1/4 of this, I take 2.5 units of this. Actually, my total weight is well under my capacity of 20, it's only 16.5. And if I add up half of 25 plus 1/3 of 24 plus 1/4 of 15, I get 24.25. On the other hand, I can take all of the first bag. I can take that uses up 18, so I have only 2 units left. So I take 2 by 15 of this bag and fill up my bag of 20, and I take nothing of the third chemical, and I get a value of 28.2. Or I can take 0 from the first one, 2/3 of this, which is 10, and all of this, which is another 10, get 20, and the value is 31. Or I can take all of this, which is 24, 15 units for 15 weight for value 24, and that leaves me with 5. So I take half of this 10 and I get 31.5. So depending on which combination I choose, clearly the value changes. In this particular case, actually this does turn out to be the optimum. It's not only, so this is not all possible. Of course, there are many other combinations which we have not listed. These are only a sample set of feasible solutions, but it so turns out that among these, the fourth one is actually the optimal solution. So before we try to examine a greedy strategy, let's make some very obvious observations. So the first observation, let us call these lemmas. Okay, so the first observation is that if the total weight, okay, that is W1 plus W2 plus Wn is less than or equal to M, right? So if the total weight of all the chemicals that I have is less than or equal to M, then there is nothing to prove, right? So the optimal solution is in fact one which sets all the exercise to 1. That is, I pick everything and take it because that's the best way to maximize the thing and I have no capacity problem. So so we will therefore assume that this is not the case. So we'll assume that M is bigger than the summation of all the Wi's. Okay? Because if M is not, M is smaller than all this. Right? So if M is bigger than or equal to all this, the summation of Wi's, we have no problem to solve and we don't need to worry about it now. Now the second observation is that any optimal choice, okay, must have weight M. Okay? That's because if the knapsack is not full, adding any chemical, it doesn't matter whether it's the best choice or not, adding any chemical increases its value, so it cannot be optimal. Of course, we are assuming that all the chemicals have non-zero value. If you have something which is worth nothing, then of course you don't get anything by adding it. But in general, if we assume that this problem is interesting if all the chemicals have some positive value. So if the knapsack is not full, then adding any chemical increases the value, so it cannot be optimal, right? So if we go back to the previous thing that we looked at, the situation where we have only 16.5 in our knapsack can never be optimal. Okay, so we must get up to 20. Among 20 we have different choices, but we must at least get up to 20 before we can even hope to be optimal. Okay, so here we have just reminded ourselves of the problem. So we have these three chemicals, 1, 2, 3, and we had these 4 different solutions that we have proposed. And now let's look at some potential greedy strategies. So we have two quantities that we are looking at, value and weight. So we can try each of them as an optimization parameter. So the first possibility is to choose highest value next. Right? So if we choose the highest value next, then what we would do is we would first start to put in item 1 because it has value 25. After we fill up as much as we can of item 1, then we would move to item 2 because it has value 24, and then we would move to item 3 because it has value 15. And if you look at it, this corresponds to this choice. So we filled up 1 first, then we filled up 2, and then we filled up 3. But as you can see, even among the examples that we have considered, this is not the best one. Okay? So we can look instead to fill up the bag so if you're looking at weight, what you want to do is keep as much capacity as possible. So we fill up the bag in order of weight, but in ascending order. So we choose the smallest weight next. We want to put as many things as we can into the bag, as many bags of chemicals as we can into our knapsack. Okay? So in this case, the smallest bag is 3, so we start with 3, then we move to the next smallest bag, which is 2, and then we move finally to the biggest bag, which is 3. Okay? And this corresponds to choosing 1 for x3 and then as much as we can of x2, and then we can't fit x1. So this is actually the third row in our table here, and again we see that this is not optimal. Right? So what we see is that either choosing only value or only weight as our criterion for picking the next item is not going to help us achieve an optimal solution, because we've already seen in this limited space of solutions that these two are not optimal. So it turns out that the correct thing to do is to combine this. So you want to look at the ratio of value upon weight. Right? So you want to say, if I take 1 unit of a particular chemical, what is the value that I will get for that 1 unit, and that because that is determined by the overall the kind of unit cost. We're really looking at the unit cost, right? So if we compute unit cost, for example, here the unit cost is 25 by 18. Okay, here it is 24 by 15, which is actually 8 by 5, and here it is 3 by 2, right? So if you look at this particular thing, so if it is you will see that actually in this case, this is the highest unit cost, okay, and then this is the second highest unit cost, and this turns out to be the third highest unit cost, right? So in this strategy, you will first pick chemical 2, then you will pick chemical 3, and then you will finally, if you still have space, you will pick chemical 1, and this corresponds in our example to the last choice. And it turns out that this strategy of picking in terms of unit cost or in terms of combining the ratio, okay, choosing the ratio with highest value to weight next, is actually the optimum greedy strategy. Okay, so in this case, we are actually going to show that our greedy strategy is optimal. But before this, we will look at some issues involving Knapsack. In particular, we will first look at applications. Okay, so Knapsack is actually quite an important problem, and it arises in many situations. And typically, an application of Knapsack requires you to choose an optimum mix. Okay, given a fixed budget. So you want to choose from a menu of options, but you only have a fixed budget to choose from. So the fixed budget is your knapsack, and the mix of options is what is available to you, and there is a certain cost or a value, depending on how you interpret it, of the different items that you have to choose. So there are many real life applications where this kind of problem arises. One of them is when you want to choose how to say consume raw materials. So supposing you have some sheets of plywood or something, and you need to cut them up in order to make some object. Then when you cut a piece of plywood, of course, the remaining piece is now less useful because it is smaller. And so there are certain costs associated with this. And if you frame it properly, you can make these kind of problems into knapsack problems. Another situation is in finance. So if you are a banker and you want to assemble a portfolio is a collection of investments of different types. So you might want to have certain mutual funds, certain stocks, certain debentures, and each of these has a cost, and you have a budget. You have so much money you want to invest, and you want to get an optimum mix. You have some costs associated with risks and returns, and this again becomes a knapsack problem. So one of the important things to realize is that we have used this possibility of fractional allocation. That is, we are allowed to take any arbitrary amount from each of the bags that we have considered, and this is a fractional allocation which allows a greedy solution. Now in many applications you don't have this, so you have what is called a 0-1 knapsack. Okay, so you have to take all or nothing of a particular object. An example of this would be the problem we looked at right at the beginning, which was to put cartons in a container. Now you can't put half a carton in a container, so you either have to choose a carton or you don't choose a carton, and you want to maximize the choice of cartons as a 0-1 knapsack. Now the problem with 0-1 knapsack, unfortunately, is it is not known to have an efficient solution. In fact, 0-1 knapsack falls into the category of problems which are called NP complete, and so it is very unlikely that there is an efficient solution. So in some sense, one has to live with the fact that you have to do the naive thing of trying all possibilities, or look for approximate solutions which might give you something which is not quite optimal but good enough in practice.